Hello, I thought I'd do a quick video to explain some of the benefits of a grounded wiper potentiometer configuration in a power supply feedback network. This was raised recently in some comments on Hackaday, and somebody was asking about just why this sort of configuration would be used. So let's consider a typical power supply here. We've got an input voltage Vin, a ground 0 volts, and an output Vout. So loosely speaking, that could be 240 volt mains in and 12 volts out. Now, how do we regulate the output voltage? Well, most power supplies will sample that through a resistive divider. Let's call that V feedback, the feedback voltage. And the power supply will adjust V out until the feedback voltage is equal to some internal reference voltage. So, for example, in practice, say this was a TL494 driving a switch mode power supply. The control chip, the TL494, would vary the duty cycle of the bridge transistors, which in turn varies V out, until the feedback voltage equals the internal reference voltage, which is typically 2.5 volts for a TL494 supply. So if we call these R2 and R1, what's the output voltage? Well, this is a simple resistive divider, so V feedback will be R1 over R1 plus R2 times V out. So if we rearrange that, we'll get V out is equal to R1 plus R2 over R1 times the feedback voltage. And at steady state, the feedback voltage is the same as the reference voltage, so that's Vref. Whoops, spotted an error there, that's R2, R1 plus R2. So simplify that and you get V out is 1 plus R2 over R1 times the reference voltage. Now, if we want an adjustable output voltage, there's two things we want to achieve. Firstly, we would ideally like a linear adjustment range, so when you turn the potentiometer knob you get an output voltage that varies linearly with knob position. And secondly, an element of safety. If the potentiometer wiper leaves contact with the track, we want the output voltage to be forced low rather than being forced high. So let's consider the simplest possible feedback arrangement involving just a single potentiometer connected between V out and 0 volts, with the wiper taken as the feedback. And it's connected such that clockwise direction causes the wiper to move closer towards 0 volts. That's equivalent to two resistors, V feedback, of values XR and 1 minus XR, where R is the total resistance of the potentiometer and X is the fraction along the track which the wiper is currently at. So X can be between 0 and 1. If we substitute these values into our general equation from the first sheet, we get V out is 1 plus R2 is XR and R1 is 1 minus XR times V ref. Cancel them and rearrange, simplify that, we get V out is 1 over 1 minus x times V ref. So if x is 0, the knob is turned fully anti-clockwise, V out is V ref. So the minimum output voltage you can achieve is the reference voltage, for example 2.5 volts. As x approaches 1, this will eventually approach infinity. So obviously the response is far from linear. In addition, if the wiper lost contact with the track, the wiper would essentially be floating, and since the feedback input on most control chips is high impedance, you've basically no idea what voltage that would settle at, so the output voltage is unpredictable. So on both counts, this is not an ideal situation. Let's look at another configuration using a potentiometer and a single fixed resistor. For sake of argument, let's put the fixed resistor in the upper leg and the potentiometer in the lower leg. And I'll connect the wiper like so. V out 0 volts, V feedback again. And clockwise travel again takes the wiper towards 0 volts. Converting this into two single resistors, like before, we have, that's R2 and that's R, we have R2 on the upper limb and 1 minus X times R on the lower limb, feedback. And if we substitute that into our equation, we get V out is 1 plus R2 over 1 minus X R times the reference voltage. And without going into too much detail again, that is again non-linear because the X term is on the bottom line. So on that account alone we can discount that. Let's instead put the variable resistor, the potentiometer, in the upper leg. So we have a resistor there, 0 volts, V out, and our potentiometer this time is in the upper leg, R1. Again, clockwise motion moves the wiper downwards. Converting that into two single resistors, we get XR on the top and R1 on the bottom. V feedback there. Substituting that in, we get V out equals 1 plus XR over R1 times V ref. Now we're getting somewhere. This time we've got X on the top line, so V out will be linearly proportional to the wiper position. When X is 0, V out is V ref, as before, that's the minimum output voltage you can possibly achieve. And when X is 1, the output voltage is 1 plus R over R1 times V ref. And the supply will be linearly adjustable between these two values. So that satisfies the linearity requirement. If the wiper leaves the track, the value of the upper resistance here goes to R, the maximum amount, because this part of the upper resistor is no longer being shunted by the wiper. That's equivalent to X going to 1. In other words, it's as if you turned the potentiometer fully clockwise. In other words, the output voltage of the supply will be forced to its maximum value, which is not safe. Well, it might be safe, but it's still not good from a design standpoint. So although it is a linear relationship, it fails on account of the safety issue with the wiper leaving the track. So that also fails. Naturally, I'm building up to the last option, which will work. And the last option is the slightly unusual grounded wiper configuration. Not exactly grounded wiper, but, well, you'll see. We have a potentiometer here going to V out. That end goes to the feedback, and the wiper goes to ground via a fixed resistor, R1. This again has a total value of R, and the clockwise direction is that way. So this looks a little bit odd, but let's simplify it. Let's split the potentiometer into two resistors first of all. That's R1, V feedback, and this resistor is XR, and that resistor is 1 minus XR. So we've got a potential divider from V out to ground consisting of XR and R1, and then a series resistor of value 1 minus XR going to the feedback pin. But since the feedback pin is usually very high impedance, the presence of this resistor will have zero effect on the feedback voltage, so we can basically forget about it. And simplify this further to a simple divider like this, where we've got XR on the top and R1 on the bottom. And that's V feedback. Now this is exactly the same as the situation when we had the potentiometer in the upper leg of the previous case. So the output voltage will again be V out is 1 plus XR over R1 times V ref. So again it will be a linear response. However, the difference this time is what happens when the wiper leaves the track. If the wiper loses connection, you've essentially got the feedback voltage connected directly to the output voltage via the resistance of the potentiometer. So the supply will try and force the output voltage down to the level of the feedback voltage, which is the reference voltage. In other words, it will force the output low when there's a failure with the wiper contact. So this scores on both accounts of linearity and the safety factor when the wiper loses contact. I'll admit that I've never actually seen this configuration used in power supplies. Generally, they're a more traditional voltage divider configuration like this, or simply a single potentiometer, sometimes with end-stop resistors to control the amount of travel. But this grounded wiper, or wiper to ground via a fixed resistor, is a far better solution, and I've used this in a couple of my own projects, such as the 40 to 400 volt power supply and the adjustable output power supply modification. Both of these are linked in the description down below. So I hope you found that interesting. Please let me know, comments, questions, I'll be happy to help. And as always, thanks for watching.